Hi and welcome to this tutorial on covalent bonds. So in the previous tutorial we had a look at ionic bonding between oppositely charged ions in a lattice. We learned about constructing formula, we learned about some of the polyatomic ions too. So in this tutorial, we're of course looking at covalent bonding. So we're going to see examples of single covalent bonding, multiple, dative, and a little bit about bond energies too. So the main things we're going to look at are what is the difference between single covalent, multiple covalent, and dative covalent bonding. Again, like with some of these topics at the start of the course, it's likely that you've come across this at GCSE before, but it's really important that you have a really very solid understanding of the foundations as you move into the A-level chemistry course. We want to fill in any gaps that might be there. So it's still really important to cover all of this content in detail. So, of course, a covalent bond, it's a bond formed between atoms that share electrons. And the atoms share electrons to gain a full outer shell. So we've seen that before. That's what they're always trying to gain because it's the lowest energy state. And remember, we've got an overall positive charge of the nucleus because the protons are going to give us a positive charge. The neutrons give us a neutral charge. So there we are in the center. And remember, these model images aren't particularly, of course, they're not accurate, but they are very much models. Because remember, the nucleus is very dense and incredibly small. And they're very distant from the electrons on the outside. There's a lot of empty space. So we've really supersized these subatomic particles here to make it clear for you to see. But it's not obviously accurate. And they're two-dimensional too, so there's lots and lots of problems with it. But it's helpful for us to just see an understanding of what's going on. So I've got an example here of covalent bonding happening. So just a single covalent bond. So there's our hydrogen. It's got 1 electron in its outer shell. My fluorine has got 7. So we can very quickly satisfy both and ensure they've got full outer shells. So hydrogen's only got the first shell, which only needs 2 electrons to be filled. And fluorine is onto its second and it needs all 8. And so we form a covalent bond, HF, and voila, brilliant. We've got 1, 2, 3, 4, 5, 6, 7, 8 for fluorine and 1, 2 for hydrogen. So we've satisfied that and we've shared the electrons and formed a covalent bond. Then we've got multiple covalent bonds that can form. So if a molecule is made up of 2 or more atoms, then we're going to get it. But if it's more than 2, then we've got multiple bonding. So here we've got 1, 2, 3, 4, 5 atoms, and they are going to come together to bond to form, well, methane, CH4. So we've got 4 single covalent bonds happening. So these are actually all single covalent bonds. And each covalent bond involves 2 electrons, as you can see, 1 from the hydrogen and 1 from the carbon. Carbon's in group 4, so it's got 4 purple. 4 yellow crosses, and each hydrogen gives 1 as well. So each electron from the electron pair comes from each of the atoms involved in the covalent bond. So 1, 2, 3, 4. And remember that covalent bonds form between non-metals. So we're looking in this area of the periodic table. So group 6, group 7, etc. Okay, so group 6 and 7 can also be involved in ionic bonding, so just be careful. But we're just looking at things bonding together from this area. We're not including our metals. And it's maintained by the electrostatic forces of attraction between the positively charged nucleus and the negatively charged electrons that are being shared. So again, here we've got the single covalent bonds between the carbon and hydrogens, or the fluorine and hydrogen here as well. And these are called dot and cross diagrams. And they tend to only show the outermost electron shells. Of course, carbon's got 2 electrons in its first shell as well, etc., etc. We don't show those. Otherwise, visually, it's way too distracting. It's the outermost electrons that dictate the reactivity, etc., etc. So we're only going to show those. And so during the formation of our covalent bonds, the atomic orbitals of the atoms involved overlap, as we said before. So each one contributes 1 electron to the bond. We can get multiple covalent bonds though. So when atoms share several pairs of electrons rather than just a single pair. And there's some well-known examples. And so we can have examples where there's a double covalent bond or a triple covalent bond. So an example of a double covalent bond, the one that you'll come across a lot, is oxygen. And that is why when you see it displayed, it is often displayed as such, this meaning our double covalent bond. They're in group 6, oxygen's in group 6, we've got 2 in group 6. So if they share a pair each, then we'll end up with 8 in our outer shell for each of them. So they're showing 2 pairs of electrons to gain a full outer shell. We can also get a triple covalent bond, and the most well-known example that you will come across is nitrogen, so diatomic nitrogen. And we show this as a triple bond when we're doing a displayed formula, but in dot and cross it's shown as this. So nitrogen's in group 1, 2, 3, 4, 5 electrons in its outer shell. So if it shares 3 pairs of electrons, it's going to be able to gain a full outer shell. So 1, 2, 3, 4, 5, 6, 7, 8, and the same on the other side. Finally, we've got dative covalent bonding. So it contains a shared pair of electrons donated by 1 atom in the bond only. And the most common examples are with ammonia. That will be the most common example you come across, but there are lots of examples aside from that. So we represent it with an arrow as such. Can you see this purple arrow here? That signifies to the reader that there has been a dative covalent bond. So if we wrote this out in just its displayed formulae, we'd have NH3, and then we would have an arrow for that final hydrogen, which signifies that there's a dative bond to make my NH4+. So this isn't balanced. We, of course, need to make sure that we've got that polyatomic ion balance, because if we've got a positive charge on the left-hand side, we need to overall have a positive charge on the right-hand side too. Now, aluminium is an interesting case because of where it sits in the periodic table. It's got both sort of covalent and non-covalent properties. It's very, very intriguing. And the aluminium central atom, it doesn't have to satisfy, it doesn't have to follow what we call the octet rule. The octet rule is that it's going to want 8 electrons, but aluminium doesn't follow that. So you'll notice that aluminium chloride is quite content with having just 1, 2, 3, 4, 5, 6 electrons in its outer shell. Okay, so it's an electron deficient molecule. But what can happen is 2 aluminium chloride molecules can come together to form Al2Cl6. That's what this is here. The 2 aluminium atoms are bonded through 2 bridging chlorine atoms, and that makes 1 dative bond each, and the octet of the aluminium is now complete. Okay, so there's my dative bond forming there, there's my dative bond forming there. So really interesting structure for the unusual case of aluminium. Then we can also consider bond energies. So the energy required to break 1 mole of particular covalent bond in its gaseous state. And that's what's going on here. Can we see we've got a covalent bond and we're breaking them up into just the atoms. And yeah, we've got examples all over the place. And that could be used as a measure of the reactivity of the covalent structure. So the harder it is to break that bond, the less reactive that structure may be. The lower its bond energy, the easier it is for the covalent bond to break. Therefore, the more reactive that covalent compound is going to be. And the bond energies also relies on bond length, the distance between the nuclei of the 2 covalently bonded atoms. So the shorter the bond length, the stronger the bond, the closer those nuclei are effectively and with the electrons, okay? So hence the more energy is required to break it. So you can see here, when we get down to a triple bond, those 2 atoms, they're very close together. I've got a bigger bolt of lightning here. It's showing that we need a lot more energy to break that triple bond. And also these are closer here. I need a lot more energy to break that. As more covalent bonds form between 2 atoms, the electron density increases and the nuclei are brought closer together. Again, we decrease bond length. Therefore, double covalent bonds are stronger than single and triple are stronger than double. So you can see the increase as we go, increase in strength. And you can see the increase in strength as we shorten the bond length. Okay, it requires more energy to break.